So, welcome everybody. I am Felipe Makara from the Tutorial Education Program, and today I'm gonna talk about thermoelectric coolers. I'll talk a little bit about theory, the Seebeck effect, the Peltier effect, which is the effect which permits the thermoelectric coolers, and the Thomson effect, which is another thermoelectric effect. The thermoelectric cooler in itself, the advantages, the problems of using this technology, and the uses that it has today, and a little experiment if someone wants to burn his fingers. So let's begin with Seebeck effect. Oh, of course, I didn't remember that the camera was on this side. This Seebeck effect was discovered by Thomas Johannes Seebeck, of course, in 1826. This Thomas was a German physicist, and it says that a difference of temperature between 2 points of a metal creates a difference of electrical potential. So we could transform temperature into electricity. So in searching a little in the internet, you can find this equation which relates the potential with the Seebeck effect multiplied by
Na noite de terça-feira, dia 12, Rebel.
So let's say if in this point right here we put 100 degrees, and this point 10 degrees, there will be a difference of 90 degrees, and this 90 degrees will be multiplied by the coefficient. So in this table I found in the internet, and it relationates the material that these wires or metals are made from with the coefficient that is measured with microvolts per Kelvin, but microvolts per Kelvin, so there is a little problem with it. We could generate electricity with this method, but it would be so little that it couldn't be efficient. So it's the problem with this method. Now we have the Peltier effect. It was, of course, postulated by Jean Charles Athanase Peltier in 1834. He was a French physicist, and it says that a current flowing through absorbed by one junction and revolved by the other. So it's a proposal of this. The Seebeck effect says that a difference of temperature makes a difference of electrical potential, and the Peltier effect says that a difference of electrical potential makes a difference of temperature between these 2 points of the circuit. So the temp difference is simply made here, multiplying the coefficients by the current, and the best way I could explain this effect, how it would possibly work, is with this graphic, which I found in the internet, and I found very interesting that it says that very way that the electrons push the heat and the hole.
necessário.
not inaccurate, but this is the best description they should have to make this effect happen. So the electrons push the heat as a pump on one side. We have N-type. This should work like this. No, also for Seebeck. In Seebeck effect, now push the holes on the p-type silicon and push the electrons on n-type silicon and make the current flow through here. So this is the filter and the feedback working. This but we can if we could apply let's say 1000 amperes on Peltier effect cooler. We couldn't have a difference of temperature so big. So most of the Peltier effect coolers have a maximum difference of temperature called delta T. So it push, let's say at zero, at the difference of 0 Kelvin, it pushes, let's say 58 watts from the cold side to the hot side. At the speed it goes to a bigger difference of temperature. This power that is pumped can pump the heat. It reach the 0 at 65. That means the bigger difference of the temperatures is 65 degrees. At this point, it can't push any more heat. It starts to let some heat pass by. So finally, a little bit about the Thomson effect. The Thomson effect was discovered by Kelvin in 51 and says if a current density J is passed through a homogeneous conductor, heat production per unit volume is R, that is the natural resistance of this material, times J square, and this part is the Joule's law, okay, minus the Thomson coefficient times the current times the derivation of the temperature per space. This is Lord Kelvin. So let's talk a little bit about thermoelectric cooler. Today there is most thermoelectric coolers 4 by 4 centimeters with silicone inside, silicone we could see the N-type and P-type silicone bounded with metal, arranged in a way which the heat is absorbed by one side and rejected by the other. But one thing is still to say about the thermoelectric cooler is that it can be a cooler and a heater at the same time, because if you remember the formula of temperature, if this current here is negative, what means that I'm throwing current and in a different way, the difference will be reversed. this side because we are broadcasting in the internet right now. So if this current right here is inversed, the temperature potential is inversed too. So it will make one side cool and the other side hot. And if we turn the wires, it will make the first side hot and the other side cool. So let's come back to that. So let's talk about the advantages of this type of cooler. The first is size. Okay, if you are going to put something little, it's perfect. You will not put this compressor right here with 5 kilograms. It's very large and it's very have a great mass. Why? Well, as I said in the preface of this presentation, by some time cooling devices were mechanical. They have moving parts, they have electric, they will fail at some time because of the electric will make the parts corrode the parts. Will make the parts horn. So there is this problem on the conventional coolers. So we do not have this problem on the filter effect coolers because it's simply N-type and P-type silicone, no vibration, only curing passing through it and hot passing from this side to this side. So it could be good, but there are the problems. The first, the fuel efficiency. Compared to a mechanic system, it has a very poor efficiency. The other thing is the size. Okay, let's imagine we make in this room, this regular room. So we would have to put thousands of plates of water cooler, and the other thing is the price. A pair of this.
Porém, 18 meses tudo vem aqui no Aliança na pracinha do
Vai stay on the mail. By $90, $9.5, free shipping. Took a month to receive. So if we put thousands of these plates, it will cost tens of thousands of dollars, and this is not good for the project owner. So it's good for other purposes. So uses now. The first could imagine of doing this with this plate, this thermoelectric cooler is mini coolers. You could cool your drink, your soda can, with just maybe sometimes powered by USB cable. So it's cool because cool little things. Other use, some people use it as processor cooler. Why? Because making a difference of temperature will make your processor cooler, or what means you can overclock your processor more easily, and you make this side hotter, which makes the heat transfer faster. And the other very specific use is with wine coolers. So the people who like wine, people who drink wine to feel the taste and the aroma of the wine, generally say that well we can't put on sunlight. You can't make vibration, you can't take off the top of it. You can make several things. The best thing for wine is to be buried and then use that. So one way to take off the vibration of the motors is by using Peltier effect coolers, so that there isn't the vibration of the motor and the wine won't vibrate in this way. So right now, someone wants to touch this little piece. I need a volunteer. Right here, someone, please. Someone wants to. Oh, 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 please come here. So, first, people who are here will read better. The reading right here. Oops. So, let's first measure how hot you are. So, here we have a code table, okay? I would say 3 millivolts of the heat coming from the atmosphere.
Abordado nas ruas.
We have 100 millivolts generate here. So it can generate energy by the Seebeck effect, of course. Now let's measure the current of it. Please look again. So it's measuring for, let's say, 5 milliamperes. So it puts 5 milliamperes by 50, I said, 50 millivolts. It's not that thing, but it generates energy. So this guy here isn't cool, isn't hot, as I said. So right now I'm going to make something more sense. So you are going to talk. Can be. What feeling this makes? Okay, let's burn some fingers right now. Okay. Now let's polarize it in the other way. And what happens? Okay. What happened when I polarize? Okay. As you can see, it can act as a cooler or as a warmer as well. So thank you to my partner here. Applause here, please. We can come back to that. So it ends my presentation. So now it's time for questions. Please raise your hand. So Jagger right there can put the microphone, bring the microphone to you. Let's make the internet spectators listen your questions. I hope you have questions. Well, in truth, not. But not on really, but that. Okay. This technology is already in use, or just for this technology is already in use, or it will just say for 1 year or two will be on the market for as coolers. Use. Um, so, Felipe, it's broadcasting. So, I don't have a news about uh, when it started to begin to be produced with silicone, but um, uh, it's not so new. You can see we have already uh, various types of coolers which can use. This photo is pretty old already, and the theory is old also. It's 1830. I think in that epoch there wasn't semiconductors. There wasn't the knowledge about semiconductors. So as you can see, the theory a mass production date of it. Um, uh, hand by hand. Let's pray for it to work. É bom. Uh, so I don't think I don't find uh, 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 good explanations. Okay, no, it's after here. I didn't find good explanations right here. I just find some illustrations to make the person to think of it. Shut up. Here, shut up. Is like we have electrons flowing through the N-type silicon and holes flowing through the P-type silicon, or what means that electrons are flowing on the other side. So these electron holes bring the heat, pump the heat from one side to the other. that it's basically the same thing a compressor makes. It pumps the heat from inside to outside and put some energy in this cone. I answer your question. Thank you. No, I couldn't inform that. I didn't find any reference on polymeric materials this way. Today, the most you buy on Mercado Livre and eBay, it's with silicone, N type and P type. Any more on the internet? Let's hear. Okay. First, let's say about the efficiency. Paulo Toba era o Paulo Toba? Ricardo Toba. Sou o Ricardo Toba. So, yeah. So, as I said, it has a bad efficiency. When if I open a datasheet for this one, in example, if I open the datasheet for this one, you would find that its maximum voltage is 12 volts, 36 volts. Its maximum voltage is 13.6. Its maximum current is about 6 amperes. So the maximum current, the maximum power dissipated is about 91 watts. 91 watts. It's better? But broadcast is better? Okay. So it costs almost 100 watts to take off 58 watts on this graph. It costs like 100 watts to take 60 watts from the hot side. The mechanical type of cooler. And about the relationship of the temperature by the power consumed. I didn't make tests, and the datasheet doesn't seem at last, or I didn't find it good. I didn't find some information about this. Okay. Any other questions from the internet? Felipe? No? Okay, you can make this seminar end. It's about time, 1:32. So thank everybody by being here. Where is my mouse? This is my contact. Thank you, everybody.